Hello students, welcome back. We are done with the determinants of order 1, 2, and 3. Now let's go over to the determinants of arbitrary order. But before that, some preparation. Deleted matrix. Let A be a n by n matrix. Then the deleted matrix Aij is an n-1 by n-1 matrix by removing the ith row and jth column, as you can see here. Cross out the ith row and cross out the jth column. Well, here's an example. We have this matrix here, and what is A of 2, 3? Okay, alright, not too bad, not bad at all. So that's A, and then that's A 2, 3, okay. Second row, out. Third column, out. And that's the deleted matrix A 2, 3. Here we go. Second row, third column, out, out, and what's left is the deleted matrix. It's easy. Another example, fourth row, first column, these are out, and what's left is the deleted matrix. How about A5, 2? This is not a deleted matrix. Fifth row, second column, and this entry -2 is A5, 2. How do you see the difference? This is lowercase, and those are uppercase. Capital, matrices. Small, those are entries. Now, what is A5 in superscript? Superscript, they mean the column vector, the fifth column vector. How about subscript? That means the row vector, the sixth row vector. Okay, a nice example, and we are ready to define the determinants of arbitrary order. Here we go. Here is the definition. Kind of hard to see, but here we go. So if you have a determinant, then A11, A12, A13, all these are selected from the first row, and then these are deleted matrices, and this sum with all those alternating sign is the determinant. Let's study it using an example here, and okay, here we go. Okay. Okay, let's focus upon the first row here, 2, 1, -2, 3. And 2 times the determinant. So this is A11. And then we have to take the deleted matrix here. So this 2 belongs to the first row, first column. So remove the first row and first column. And what's left is the deleted matrix that I want. Minus A12, so this second entry, 1, determinant. Now we are using this one, right? 1. So second column, out. First row, out. And what's left is the deleted matrix that I'm looking for. And then we have plus, minus, plus this number. So -2, determinant of that, and I'm using this number. So I have to remove first row and the third column. So third column out, First row out. So far so good. And finally, minus the last number 3. I'm using this, so I must remove first row, fourth column. And if you calculate this, you're going to get the determinant. Now, how do I calculate each determinant here? Those are 3 by 3, so you can do those. Or you can use the same thing and reduce each of them to 2 by 2 and go from there. So if I give you a determinant problem for about 5 by 5, then you'll have to do this to reduce 4 by 4 matrices, and there are a bunch of them, 5 of them actually, and each 4 by 4 I'll have to reduce those by 3 by 3, and there are a bunch of them, and then reduce further. Oh, this will go out of control very, very quickly. So I cannot write many problems, but you should know how to do this. I'll probably end up slipping in some determinant problem as an intermediate step, but maybe I can write just a problem like this with some large matrix, who knows. So that's a determinant, that's a definition of the determinant. Follow the first row and reduce. Now, please pay particular attention to this reduction. Determinant of order 4 can be written by a summation of determinants of order 3. In general, determinant of order n is defined by a summation of determinants of order n minus 1. This kind of definition is called recursive definition. Recursive definition. It depends upon the previous generation. Nth order depends upon n minus first order, and n minus first order in turn depends upon n minus second order, and so on and so forth. If you go backward, it goes like this. Base case, 2 by 2 case, we did it, AD minus BC. From that, we get the third order, and from the third order, we get the fourth order. From the fourth order, we get the fifth order, and then the sixth order, and then the seventh order, and we cover everything, every finite order. So this definition, this recursive definition, is actually good. It's well defined. There's a bit of a problem though. This is not the only formula to get the determinant. There are other formulas. I don't have to use the first row. I can use any other row as well, ith row, or I can use even column, jth column. All I have to do is to follow that plus minus trick. And let's go back to the same example, and this is the example we already did, following the first row here. And what if I follow the second row? That makes a lot more sense because I have a bunch of zeros here. And we have 3, 0, 4, 0, and then, for example, how about this 4? Yeah, okay, this one. So I have to remove the second row, of course, and also the third column, and what's left is this deleted matrix. And the other deleted matrices are given pretty much the same way, exactly the same way actually. From this number, remove the first column, second row, kind of like this. So these determinants are pretty much okay. And then these numbers, 3, 0, 4, 0, those are okay too. What's not okay? The sign. I begin with minus, minus, plus, minus, plus. Previously not so. We had plus, minus, alternating sign, but I started from negative. What's the difference? Well, 1, 1 is plus. And from there, as I move one step, we have changed. So plus, minus, we can go like that too, but plus, minus, now this is minus, and then plus, minus, plus. So plus, minus, plus, minus, plus. So that's it. Minus, plus, minus, plus, like that. Negative 1 to the I plus j power. So I is 2 and j begins from 1. So negative 1 to the third power, that's odd power. So we begin with negative power. If you follow this signal notation well, then yeah, you can easily understand it. But even I have difficulty following this because there are so many indices and they're so confusing. So it's much better to start from plus here and then do the alternating sign. Like this. Start from plus here and then alternating, plus minus, plus minus, plus minus. Each time I move horizontally or vertically, we have sign change. Okay, solution 2 was following the second row. How about column? This is solution 3. I just used the first column. I could have used the second column, third column, or fourth column, but I decided to use the first column. So first column here, 2, 3, 2, negative 3, 2, 3, 2, negative 3, and the signs are plus, minus, plus, minus. And then the deleted matrix is pretty much the same way. For example, this 3, we have to remove this, this second row and the first column, and what's left is this deleted matrix. So we have multiple computational formulae for determinants. They're all recursive, and you can use whatever form that suits you the best. If you have a lot of zeros in a certain column, go ahead with that column with this column formula. If you have a lot of zeros in a certain row, go ahead with this rows formula in that row. But the definition is going to the first row so that we have concrete definition recursively. For the other formulas, we have to actually prove that these are equivalent to this. And that proof is going to be done in an optional video because it can go deep very quickly. Alright, so much for the computation, and let's have some theory. The properties of determinant. Number 1, multilinear. At each column, we have to have linearity, and there are n columns. So these are n linearities put together. So it's multilinear. Goes like this. Any arbitrary column, jth column, if you have a linear combination there, ax plus by there, then we can separate it ax plus by like this. And that goes to all the columns. So it's multilinear. Another property is alternating. We can switch the order of two columns, ai, aj, switch these two, then we gain the negative sign. Here's an immediate consequence of that. If these two columns are the same, if I switch x and x, it stays the same, yet we have to earn the negative sign. Alright, what's the conclusion? What is the number that is the same as a negative of itself? Only 0. So if you see two identical columns, then the determinant is 0. Finally, the property of identity matrix. Determinant of identity matrix is always 1. The proof, we're going to do those in an optional video. Multilinearity is tricky, tedious, but we can do that. Identity, not too bad. But alternating, oh boy, this is hard. Okay, so much for section 3 of this notebook. And let's move on to the next section. There are a lot, but most of them we already considered. We can do the determinant computation using columns as well as rows. And then row-column equivalence. Because of the computational formula are identical, either to column or row, so column or row makes no difference. So the properties of the derivatives, properties of determinants, the multilinear and alternating apply for rows as well. So for example, in this row, if you put in linear combination, you can separate it. If you switch two rows, then you have negative of the determinant and so on. If you see two identical rows, then the determinant is 0, those kind of things. General determinant formula, okay. We already discussed how to use this in an example. As for the proof, later, it's too tricky. Now, determinants and elementary row operations or elementary column operations. Elementary column operations first. If you multiply a certain real number to a certain column, then the determinant is that constant c times the determinant. It follows from the multilinearity. You can take the c out. For each column, you can do that. Now, if you switch two columns, then you have negative determinant. That comes from the alternating property. Finally, the third, if you multiply a certain constant to a certain column and then add it to another column, then no change to the determinant. And of course, you can do elementary row operations, and the properties are the same because columns and row, those are equivalent. Now, this one is multilinearity, difficult to prove. This is alternating, even more difficult to prove. But using these two, we can prove this one, and that's what we are going to do here. So we have AI plus CAJ in ith column. So we can separate those using the multilinearity. AI plus C times AJ there. We have linear combination separated out. Now we have AJ and another AJ. So the determinant is 0. So this part just drops out. And then what do we have? The determinant of the original. So we have what we want. If you multiply a certain number to a certain column and add it to another column, no change. Same for the rows. Next property, determinant preserves the matrix multiplication. Determinant of AB is determinant of A times determinant of B. Determinant of transpose stay the same, and that's easy because of those column-row equivalents. Determinant of inverse is a reciprocal of the determinant and consequently non-invertible if the determinant is 0. And that's easy because A inverse times A is I and determinant of I is 1. We can apply this. The detail is left to the students. Finally, the uniqueness. If there's any map from vector space to the real number system with multilinear, alternating, and the identity property, it has to be the determinant, the uniqueness. Why? It's significant, but it's difficult, so I'm not going to do that. I'll do those in optional videos. And that completes sections 3 and 4.